Now we'll start talking about diamagnetism. And let's first review the contributions to the atomic magnetic moment. So we have for contributions to the atomic magnetic moment, first we can list the electron spin. Electron spin gives us a contribution, as we have seen. The magnetic moment mu s is equal to minus lambda factor Bohr magneton times m sub s. And remember, this lambda factor for spin only is approximately 2. We have electron orbital angular momentum that is contributing. Now we have the magnetic moment due to the orbit, mu orbit, let's say, is basically minus Bohr magneton times the magnetic quantum number m sub l. And in the presence of both spin and orbit, we have a total contribution minus lambda factor g Bohr magneton m sub j, and g is, if you remember, 1 plus jj plus 1, etc. So it's it depends on the relative contribution of spin and orbit. And g factor for orbit only is 1. Okay, and there's one more contribution we haven't talked about, that is the change in the electron orbital motion when an external magnetic field is turned on. This is due to Faraday's effect. So we can have a possible change in electron orbital motion in the presence of an external magnetic field, or more specifically we can say when the magnetic field is turned on, there will be a change in the electron orbital motion, and this is going to give us a change in the magnetic moment delta m, which is going to be in such a way that it's going to oppose the change in the flux, and it will, as we will show, it will lead to a diamagnetic susceptibility. Susceptibility, remember, is the response of the material to external magnetic field, magnetization divided by magnetic field. It's given by minus the atomic number z, electron charge square, average radius of the orbit squared, mu 0 h divided by 6 times mass of the electron. Obviously I have mu 0 here. This is given in SI. So we're going to derive this actually in the next video. Now what I want to focus on is how to detect this diamagnetic behavior, and there is something we know about the diamagnetic behavior, that is the susceptibility is low. And this effect, because all atoms have electrons orbiting, if you turn on external magnetic field, this effect has to be present in all materials. So let's make a few remarks here. So the first one is diamagnetic effect, first of all, is present in all materials, but is much weaker than ferro or paramagnetism. So the effect is there, but it's just not detectable because it's much weaker than the other types of magnetic response. And if an atom has no magnetic moment, basically it's a closed shell structure. It has no magnetic moment contribution from orbit or spin. We're talking about closed shell structures. Then it is a diamagnet. All noble gases are, for example, diamagnets. Now I want to look at the experimental detection of the diamagnetism. So a good example of diamagnetic material, strongly diamagnetic material, is bismuth. So if you make a bismuth rod and insert it in between the poles of an electromagnet, the north pole and south pole, what will happen is that you will have induced north and south poles on the bismuth. So this is a bismuth rod. So when I put it inside this electromagnet, normally what would you expect? You would see that the north pole would be attracting the south poles. So on the left side you should see south poles, on the right side you should see north poles forming, but because it's a diamagnet, we see the opposite response. So we basically see that we have induced north poles on the left side, and then we have induced south poles on the right side. So as a result, you have a repulsive force from the north pole here. So you feel a force that is repulsive due to the north pole, and then you feel a repulsive force due to the south pole of the electromagnet. Since Fs will be equal to, in magnitude, it will be equal to Fn, basically this bismuth rod will not move. So you will see equal and opposite forces. This actually leads to levitation of bismuth. There's a nice demonstration in a YouTube video. I have put a link to this one, so I suggest that you also take a look at this experimental demonstration. But one way to show that it is a diamagnet is to have a pointy pole on one side, so that you have a non-uniform field distribution. And in this case, the equality of the forces will not be true anymore. So you will have the force due to the south pole will be dominating over the force due to the north pole. So you will see that in this case, Fs will be greater than Fn, and bismuth swings closer to the north pole of the electromagnet. And it basically expels the flux by moving to the low field region. So this is expelling by moving to the low field region. So that's one way to show that a material is diamagnetic. One, there is no force. Well, there is no net force if you have a uniform magnetic field. If you have a non-uniform magnetic field, then it will be attracted to the part that has the low field region. So in that case, we can basically be sure that it is a diamagnet. So we talked about contributions to the atomic magnetic moment. We have spin, minus G Bohr magneton ms. Bohr magneton was EH bar over 2 mass of the electron, remember. And the lambda factor G is 2 for spin, and ms is 1/2. So for a spin, 1/2. Then we would have a Bohr magneton contribution from spin. For electron orbit, we have the lambda factor equals 1, and it's minus Bohr magneton m sub L, the magnetic quantum number. That's the orbit contribution. The change in electron orbital motion when a magnetic field is turned on is going to cause a change in the magnetic moment, and the diamagnetic susceptibility that results is given by this expression in SI, as we're going to prove in the next video. And this effect is present in all materials because you will have a change in electron orbital motion when a magnetic field is turned on, but it will be only the dominant factor if the atom has no net magnetic moment due to spin or orbit. That's a closed shell structure. Then it is going to be a diamagnet. Bismuth is a good example, and the experimental detection basically is as follows. So we can put it in a uniform magnetic field, and we should see no motion because the net force will be 0. If it was at rest at t is equal to 0, then when you turn on the magnetic field, it should remain at rest. Or if you have a non-uniform field distribution, it will move towards the low field region, and this is basically going to prove that you have a diamagnetic material.